This will be an overview of the beginning of Chapter 4 regarding mass and energy balances. With any mass balance problem, there are some fundamental steps that you need to take to solve this exactly. First and foremost, just label all the streams with a unique name. It could be numbers, it could be names, but make sure that they all have a unique name. And before doing any other calculations, if you're given any flow in volumetric flow rate units, like gallons per minute, liters per minute, cubic meters per hour, remember first to convert it into a mass flow rate using the density of the fluid that you are balancing. You cannot do a balance with volumetric flow rates. You must convert to mass first. After this, determine how many individual components are present in the unit that you wish to perform the mass balance. After counting these, this would be the maximum number of independent mass balance equations you can write for the system. Determine the degrees of freedom for the problem. If there are more unknowns than equations, then look for more information in terms of other equations that you can use so that you can have the degrees of freedom equal to 0. Once this is established, then solve the equation simultaneously using algebra. Let's take a look at this example problem where we're going to treat metal using an acid bath, which is called a pickle bath, and the metal will then be washed. The way it works is the two baths will be present, one having an acid solution and the second one having a dilute aqueous solution as the wash bath. Steel, for instance, is rolled into the pickle bath where it gets treated with the acid chemical present there, after which it then goes through a wash bath where fresh water rinses it off and the steel is now passivated. Now there's a number of places where liquid can be transferred in this problem. One is where the steel actually picks up some liquid from the pickle bath and it is carried over into the wash bath. And likewise, in the wash bath, the steel leaving it also contains some liquid on it. And in this problem, we're going to say that it's 1 kilogram of liquid for every kilogram of steel. And the steel flow rate in this problem will be 1,000 kilograms per minute. Our target concentrations in the pickle bath are 30% by mass sulfuric acid. We also have an upper limit on the amount of dissolved iron which is removed from the steel, and that concentration is 500 parts per million. Over in the wash bath, the acid must be diluted down to a maximum of 0.1% sulfuric acid on a mass basis. To make up for any acid losses, we have a concentrated sulfuric acid solution, which is 90% by mass of H2SO4, and the balance being water. On the wash side, we have fresh water, and that has only water. There is no acid involved at all. Some of the wash bath solution is recycled back to the pickle bath, and this will be used as dilution water to take that 90% concentrated solution to the targeted 30%. We also must allow for some purging to be done in case we have more fresh water needed than is required as dilution water for the pickle bath. Similarly, we lose iron in the pickle bath at a rate of 0.5 kilograms of iron for every 1,000 kilograms of steel. And this will necessitate the use of a purge on the pickle bath so that the iron levels do not build up. This problem is a little easier to look at if we just focus on the liquid side of it and ignore the steel side. So we have a concentrated sulfuric acid solution, 90% coming into our pickle bath. Leaving is the pickle purge. Also entering the bath is the liquid from the wash bath. Fresh water is added to the wash bath, and then there is some wash purge. Now there is some liquid carryover from the pickle bath into the wash bath due to the metal traveling through the tube, and we can put in streams of that carryover from the pickle bath and also from the wash bath. Now we want to number our streams, and we do it sequentially. But remember, we have one more stream that we haven't considered, and that is the stream of dissolved iron. And so we're going to call that stream 8. Even though steel comes in as a solid, there is a portion of that steel that gets dissolved, and that will be that, stream 8 will be that fraction that is dissolved. Let's take a look at some of our mass flow rates that we do know. The stream of number 8 would be the 1,000 kilograms of steel per minute. Of that, there is 0.5 kilograms of iron dissolved for every 1,000 kilograms of steel processed. So the mass flow rate of stream 8 is 0.5 kilograms per minute. Likewise, in stream 3, we have 1,000 minus 0.5 kilograms of steel per minute flowing through the pickle bath. There is 1 kilogram of liquid carried over for every 1,000 kilograms of steel, and that turns out for stream 3 to be 1 kilogram per minute. A similar thing can be calculated for stream 6, and it is also 1 kilogram per minute on its flow rate. Now let's take a look at the mass balances around the pickle bath. We have 3 components: sulfuric acid, water, and dissolved iron. So we can only write at most 3 independent mass balance equations. So let's take a look at the total mass balance equations surrounding the pickle bath. We have 3 inlet streams, that being the concentrated sulfuric acid, stream 1, the recycled wash bath solution, stream 2, and the dissolved iron, stream 8. Leaving our pickle bath is stream 3, the carryover of liquid into the wash bath, and stream 4, which is the purge of the pickle bath. We can do an iron and sulfuric acid balance as well. For the sulfuric acid, my concentrated acid coming in stream 1 is just its mass fraction, 0.9, times the total flow rate, m.1. Our wash bath solution, we know it is a maximum of 0.1% sulfuric acid. So let's set that as a fixed number and solve the problem using that information. So coming in stream 2, 0.1% is 0.001 mass fraction, and we'll multiply that by the total stream 2 flow rate, m.2. And then that will equal the sulfuric acid leaving in streams 3 and 4. And in the pickle bath solution, the concentration of sulfuric acid is a 0.3 mass fraction. We can also do a dissolved iron balance. Iron comes in stream 8, which is the mass flow rate of stream 8, which we determined to be 0.5 kilograms per minute. Some of it comes in with stream 2. We're going to use the mass fraction of iron in stream 2, which we do not know, and multiply that by the mass flow rate of stream 2. And that should equal what's leaving. Well, we are targeting a concentration of 500 parts per million of iron in the pickle bath solution. So its mass fraction is 500 divided by 1 million. And we'll multiply it by the sum of the 2 flow rates, M3 and M4. Let's look at our unknowns. We do not know the flow of M.1, nor do we know M.2 or M.4. And we do not know yet what the concentration of iron is in the wash bath solution that's being recycled. So we have a total of 3 equations and 4 unknowns. So at this point, we cannot solve the pickle bath uniquely. Let's now take a look at the wash bath. Again, a total balance. We look at the streams entering, which will be streams 3 and stream 5. So a total balance would be m.3 plus m.5. And leaving our wash bath, we have m.6, m.7, and m.2. We can do sulfuric acid balance. Stream 3 contains all the sulfuric acid entering the wash bath process, and it is at a mass fraction of 0.3. And then leaving our wash bath, we have a concentration of 0.1% or 0.001 mass fraction, and we'll multiply that by the 3 streams leaving, M6, M2, and M7. Also, an iron balance. Stream 3 contains the only iron entering the wash bath system, and its mass fraction is 500 divided by 1,000,000. Multiply that by m.3. And then leaving is the mass fraction of iron in stream 2, which is also the same concentration as the mass fraction of iron in stream 6 and stream 7. And those will be multiplied by the 3 flow rates, and that will equal the iron leaving our system. We pick up 2 additional unknowns, that is the fresh water and also the flow rate of liquid in the wash purge, m.7. So we have a total of 6 unknowns, but we do have 6 equations, so we can solve this problem uniquely. We're now going to solve these equations, but we're going to start with the wash bath first. So let's look at the mass balance equations. And instead of using the numbers for mass fractions, I put in variable names. So for the sulfuric acid, for instance, X with subscript pickle is the mass fraction of sulfuric acid in the pickle bath, and X subscript wash is the mass fraction of sulfuric acid in the wash bath. Similarly, with iron, X Fe pickle is the iron concentration in the pickle solution, and X Fe wash is the iron concentration in the wash bath. Notice in all 3 equations I have M2 plus M7 in each one of those places. I do know M6 already, so I'm going to use the total balance and solve for M2 plus M7, and that will equal M3 plus M5 minus M6. I'm going to substitute that value into the iron mass balance equation and find out that the flow rate of stream 5 will equal the flow rate of stream number 3 times the ratio of iron in the pickle solution divided by the mass fraction of iron in the wash solution minus 1. And doing a sulfuric acid balance, I can determine what the iron mass fraction in the wash solution is given by that of the pickle solution multiplied by the mass fraction of sulfuric acid in the wash solution divided by the mass fraction of sulfuric acid in the pickle solution. So now I can determine all the flow rates in the pickle bath except for M2 and M7 uniquely. I can only determine what the sum of those 2 are, but I can determine M5 and the mass fraction of iron in the wash solution. Now we're going to do the pickle bath mass balance. Again, we have the mass balance equations, and I substituted in for the sulfuric acid concentration in the stock solution its mass fraction I label as X sub CONC, which is that 90% concentration. Again, I'll use X wash and X pickle to refer to the sulfuric acid's concentration in the wash and pickle solution respectively. And also in the iron in the wash would be X Fe wash, and the mass fraction of iron in the pickle solution would be X Fe pickle. Let's rearrange the total mass balance equation so that we can get an equation for M4, and that's just equal to M1 plus M2 plus M8 minus M3. We can then substitute that value for M4 into the sulfuric acid balance equation, And after a little bit of algebra and rearranging, we get an expression for m dot 1 as a function of the pickle and concentration, the concentrated acid concentration, and the wash concentration of sulfuric acid, the mass flow rate of stream 8 and the mass flow rate of stream 2. And then using that equation, substituting it into the iron mass balance equation, we get a unique equation for the mass flow rate of stream 2 in terms of mass flow rate of stream 8 and the sulfuric acid mass fractions and the iron mass fractions in both the pickle solution, the wash solution, and the concentrated acid solution. So now I can solve for my flow rate of stream 2, substitute that in and determine the flow rate of stream 1, and then determine the flow rate of stream 4. And then once that is known, I can then determine what the balance is on the wash bath. So let's take a look at what Excel gives us. Here's a sample of the spreadsheet where I have for the concentrated solution is 0.9 mass fraction of sulfuric acid. The mass fraction of iron in the pickle solution is 5 times 10 to the minus 4, which is equivalent to 500 parts per million. I set the wash solution to be 0.1% or 0.001 mass fraction of sulfuric acid. The pickle solution target is 0.3 mass fraction for the sulfuric acid. Stream 8 has a mass flow rate of 0.5 kilograms per minute. Stream 3 and 6 are both 1 kilogram per minute. I can then solve for the mass fraction of iron in the wash solution is 1.67 times 10 to the minus 6, which is equivalent to 1.7 parts per million. Using that value, we can determine that the flow rate of stream 5 is 299 kilograms per minute. And that will be also the sum of the mass flow rate of stream 2 and stream 7. I can then determine what the mass flow rate of stream 2 is, and it turns out to be 668.39 kilograms per minute. Back substitute that in for the mass flow rate of stream 1, we get 333 kilograms per minute. Then stream 4 would total 1,001.23 kilograms per minute. We then go back to determine what the mass flow rate of stream 7 is. And notice that it is a negative 369.39 kilograms per minute. Now, assuming our algebra is correct, the only thing that we had done was state that the wash solution had a mass fraction of sulfuric acid of 0.001. But that was just the maximum mass fraction of sulfuric acid. We can go less. In fact, we have to go less. Otherwise, we will not have enough diluting water from stream 2 to take the concentration of the acid from 0.9 to 0.3 in the pickle solution. Redoing our mass balances, I allowed my wash solution mass fraction of sulfuric acid to vary, and I adjusted its value such that when we calculated our flow rate of stream 7, it is identically equal to 0. And so I had to lower that mass fraction from a value of 0.001 to a value of 0.000449. Doing so, we find that our flow rate of stream 5 is now 667.17 kilograms per minute. So that's our fresh water requirement. The amount recycled back to the pickle bath and then to is 667.17. We'll need 333 kilograms per minute of sulfuric acid from the concentrated stock. M4, which is our purge, will be 1,000 kilograms per minute from the pickle tank, and then that will leave the flow rate of stream 7 to be identically equal to 0.